Looks very good. Ok. Hola a todos. Muchas gracias por estar ahora con nosotros. Ya hablé con Glenn que voy a hacer la introducción en español, así que él está informado. Glenn, I already informed you that we'll speak Spanish, so no problem. Hoy día, como les hemos anunciado, al fin logramos hacer esa reunión junto con Glenn, que nos está acompañando desde Australia. No ha sido tan fácil porque tenemos muchas horas de diferencia. En Australia en este momento son las 9 de la mañana, aquí son las 7 de la tarde. Entonces, como el mejor horario que logramos encontrar. Sabemos que hoy día además es feriado, así que gracias por su interés. Me gustaría comentarle primero un poco, porque con Glenn realmente encontramos una persona, como se llaman los multitalentos. Tuve la oportunidad de hablar un poco con él antes de que ustedes entraron, y él se dedica, en realidad tiene 3 empresas donde está trabajando en este momento en Australia, y que hacen realmente de todo lo que nos imaginamos en el sector solar. La primera empresa, se me fue justamente ahora, es SmartEnergyLab, donde se dedica básicamente a capacitaciones y a pruebas en terreno. Entonces hacen muchas capacitaciones, especialmente ahora, yo creo, con el COVID uno puede ver que tiene un estudio más o menos preparado ahí para hacer los entrenamientos. También tiene una empresa que se llama SolarQuip, que es una empresa que hace ingeniería para proyectos solares, ¿ya? No sé, básicamente una empresa de asesoría e ingeniería para distintos tipos de proyectos. Y como si no fuera suficiente, también tiene una empresa que se llama Solaris, que hace un software que es Solar Plus. Todo eso él nos va a explicar más allá en su presentación, pero creo que es interesante conocerlo. Él tiene conocimiento en electrónicas, energía renovable, desarrollo de software, web hosting, y claramente también en entrenamientos y capacitaciones. Y realmente parece una persona apasionada por el tema de la energía renovable y poder compartir su conocimiento. Así que como pequeñas introducciones en la presentación, por favor mantengan todos el micrófono en silencio para no interrumpir. Las preguntas sería perfecto hacerlos por el chat, ¿ya? Glenn va a hacer de vez en cuando una pausa y yo voy a tomar la oportunidad para poder leer las preguntas que tienen. Eso, como les digo, vamos a hacer de vez en cuando entre medio. Yo, bueno, a mí me conocen, soy David Rao, director ACESOL y también presidente en el Comité Fotovoltaico, y nos acompañan varios directores también de ACESOL, está la Marcela como siempre. Entonces ahora voy a cambiar a inglés para darle la introducción también a Glenn. Okay, Glenn, sorry, that was the part in Spanish. I just explained about the questions, about the microphones, and I gave the short introduction on yourself. I already did it, but I would like to come back and really appreciate you for your time and for the opportunity to listen to your presentation today. I think it will be very, very interesting for us. And I already heard that everybody is looking forward to get to know you. So I hope we will have no technical issues, and I just switch to you. So welcome.
Thank you, David. And hola, everyone. I'm afraid that's the limit of my Spanish. So I think David's already explained that to view large screen, you'll need to have speaker view as opposed to having me as a little thumbnail. The presentation that I'm giving today will cover a bit about Australia, a bit about solar in Australia, just to contrast how it is in Chile, and then look at some system design considerations, particularly in the residential market. That's where I do most of my work, is residential and commercial systems. So I'll be talking about system configurations. I'll also be talking about battery systems and some of the safety standards in Australia that we've introduced for batteries. Now, we don't share the same standards, I presume, but you could consider them a best practice guide. But I'd like to start with just a little bit about where I've come from and my journey in solar. So I'm just going to bring up my presentation here. And also, by the way, please feel free to ask questions throughout through the chat window, and I'll pass over to David to to read some of the questions out to me. So this is where I live, actually. It's a mountain just about an hour and a half east of Melbourne. It's in the Yarra Valley, and here I run a lot of training courses. So this is one of my labs. I've been running courses for about 5 years here at my facility. I'm kind of doing it because I have a testing facility, so I'm testing equipment. It also means I can use that equipment for students to train on, and it means that I can learn about all the different products that are on the market. So yeah, it's kind of like, it's a great place for me to play with technology. We've got most of the major brands available in Australia here, spread around my labs, but also spilling out into the housing co-op that I live in. So I live on top of a mountain. Here's just a clean picture of Mount Tillibawong. What you're looking at here is a cluster of 7 homes. There's actually 30 homes, all off-grid, all on one property. So we're known as a housing co-op. We're 46 years old. We have a microgrid, so we share power through our own reticulated system within our cluster. So there's about 7 homes on my microgrid at the moment. And that means that the solar from one home, any surplus can be used by another. And there's just a few of us coming together for a meeting or for a fun day. Yeah, so we're an off-grid community, 46 years without mains power. And I think a lot of my learning, because I've lived off-grid most of my adult life, has come around just living off renewable energy all the time. My background actually is in electronics. It started off over 40 years ago in electronics and ended up moving into solar because I bought a house without any power. So it's kind of learning by needing to learn. And there's my house. It's quite a modest house by Australian standards. We've got a lot of solar on it though. So really part of the purpose of covering the house with solar is to provide arrays for my testing facilities, because the testing facility is nearby, but also it helps keep the house cool in summer. So one of the side benefits of solar is actually shading. It reduces the solar impact on the building significantly in summertime. You can see there's solar on all sorts of facets of the roof there, even what's on the side, the western side of the house. Really, that's just solar shading to keep the western sun off the building, but it still generates a bit of electricity. We use PV for water heating, as well as thermal systems. They're evacuated tubes. And we have hydronic heating in the slab. So today's actually quite a nice day. It's going to get up to about 12 degrees here, but it's in wintertime, it's generally around about 5 degrees outside. So it's pretty cool. And we get a bit of snow from time to time. So that's a little bit about me. So Australia, solar in Australia has absolutely boomed. In fact, statistically, we have the highest per capita installations of solar in the world. So I think one in every 5 homes now have solar on it in Australia. Last year, there was 2.2 gigawatts of utility scale solar installed in 1 year. It has just absolutely skyrocketed. And that's because the price of solar is just so compelling. It's no longer an ideological choice for generators. They just go, well, it's cheaper. Why don't we just use solar? So we're seeing a huge growth in the utility market. In the residential market, the rooftop solar aggregate is about 2.3 gigawatts at the moment and growing at a steady rate. But what's happening as well is customers are starting to think about energy storage. Now, I don't think this is an economic decision, and people sort of come at it thinking they're going to save money by adding a battery at first, but really it's more about new technology, being able to have power independence in case of grid failure. Even though we have a very reliable grid, people still kind of fear losing power, and also owning their own solar, like not letting it leak out to the grid, but being able to store it and use it themselves. There's a kind of sense of ownership around clean energy. And I see this as a move towards what I call the autonomous grid, which is where homes can generate and store as much energy as they need. So there's a little overview of large scale in Australia as of, I think, March this year. Total 11 gigawatts of solar installed. Most of it in the sunny parts, Queensland, New South Wales, most populous and sunniest parts. But even in the less sunny parts like Victoria and Tasmania, solar is still, utility scale solar is still doing very well. Just before this webinar started, I thought I'd just check out the solar resource of Chile, and wow, what an amazing range you have from the sunniest part in the world to not so sunny part in the south. But yeah, it's you have an amazing range of solar potential. So this is a little overview of system sizes. What's really amazing now is people are putting in very big systems, way more than they actually need to produce the energy that they use. And the reason for that is it kind of makes economic sense in a strange way, because they don't need to consider the trying to deal with poor weather conditions and overcast, etc., still meeting their energy needs. By oversizing, a large system will produce enough energy on an overcast day to cover most of their consumption. So in a way, it's a way of not having to put batteries in, just putting in more solar. So during the day, almost all the energy is coming from renewable sources. So we're up to about average domestic system now, 7.6 kilowatts. There's some kind of challenges though coming forward, which is rooftop solar, of course, connected to the grid is going to interact with the grid. And what we're seeing now is solar is starting to displace a lot of daytime generation from non-renewable sources, particularly coal and gas. But they've got the challenge of the peak is early in the morning, often, depending on the weather conditions, and solar isn't really pumping very much. So the challenge is getting the mix right. And this picture shows coal is brown and black, renewables are yellow, green. There's some hydro and battery in there as well. And batteries are becoming, utility scale batteries are becoming a major part of the mix now in Australia to help smooth or firm the amount of energy supplied to the grid. Because solar being intermittent, can come and go very quickly with cloud cover. The grid needs a fairly reliable supply. So that's just a little bit of a one-day snapshot of solar on a fairly sunny day in Australia on our grid. Now I'm going to get a bit technical next, but if any questions come through, David, so far?
No, up to now, everybody is just fine, Glenn. Thanks.
Okay, good. All right. So, I imagine there's a broad mix in the audience here. So apologies for those who the technical might be a little bit dull, but I'll try to mix it up. So we've got some technical stuff coming up now. Now, because I've been working mostly in the domestic and small commercial scale, I've had a lot to do with systems which have battery storage on grid. In Australia, we call those hybrid systems. A hybrid system means it's got multiple sources, it's got solar, it's got batteries, it's got the utility. What I want to talk about is system configurations for hybrid, or more technically what we call multi-mode systems, multiple modes of operation. And I'm going to explain a little bit about what DC coupling is, what AC coupling is, how some products with a single grid port can work in multiple modes. That grid port can switch from standalone to grid tie, where some systems use direct DC-DC conversion and others so-called AC batteries, which is really just a misnomer, but it's a way of referring to something that's a integrated product that has an inverter and a battery. So I'm going to look at some system configurations. First up, DC coupled systems. Now, historically, there was only one way to charge a battery. It was with a solar panel, or one way using solar, a solar panel directly connected to a battery. And so DC coupling was the norm, and it works. It used to be very crude. Basically, a solar panel with nothing more than a simple series charge controller to stop the battery being overcharged was the way of charging a battery. Then it got more sophisticated with the development of maximum power point trackers, which allow for a variation of voltage from the array to the battery to be matched with each other. Incidentally, the maximum power point tracker, which is built into every solar inverter as well, is an Australian invention. A friend of mine's dad invented it back in 1983 and held the world patent until 2006, I think. So maximum power point trackers allow very efficient charging of battery systems from a solar source. So the pros of DC coupled systems is that even if you've got a battery with an inverter and a DC coupled charging source, which may be integrated into the same box, it doesn't have to be a separate device. If the grid's not available, you'll still be able to charge those batteries. So charging of batteries is guaranteed with a DC coupled system, irrespective of the presence of the grid. Often they're in hybrid systems, residential hybrid systems, often it's all in one solution, which means you have an inverter, you have a DC charger, you have a grid connection all in one product. And so it makes for a very easy installation. Now, there's a technical term there, IES limits, which is really an Australian thing. Inverter energy systems is a way of describing the amount of inverters connected to a single installation. And in Australia, we have limits on that. So if you're on a single phase residential system, you can only have typically 5 to 10 kilowatts of inverters connected. Now, a DC coupled system doesn't impact on that because it's not an inverter. It's actually charging batteries directly. So that's a bit of a plus. You can have a lot of solar and a small inverter interconnection with the grid. It may not require a power meter. And I'm going to explain that in a bit more detail coming forward with some diagrams. And generally, DC coupled systems, hybrid ones, will provide backup. That means they can give you power when the grid fails. And many of them also can be installed without batteries. So a hybrid system typically will work without batteries. It'll just be a pure grid tie inverter. On the cons side, they often, unless they're an all-in-one, this is an unless, if they're separate components, they're a bit more complicated. So if you have a maximum power point tracking charge controller, you have a solar inverter, you might have some way of measuring that charge current, some monitoring systems on the battery. It can get a bit complicated. And generally, all-in-one hybrid systems have quite small backup capability. They're transformerless topology with small surge ratings. Often they can only run 2.5 to 5 kVA of load on a single phase without the grid to support it. So that's a kind of summary of a DC coupled system. So David, you got any questions yet?
Glenn, yes. I have a question. It's not related to DC coupled system. It was, I think, before that. And the question is, in the on-grid solution, if the battery is limited only to supply for self-consumption, or if you are also if you can inject to the grid.
Okay. Well, we'll definitely cover that with my diagrams coming up in a second. So that's a good segue to what's next. So right. I won't answer it this very second without the diagram to explain it. So just to give some pictures of what a hybrid inverter looks like, here's a couple from my lab, the SolarX all-in-one and the Huawei all-in-one. There are many, many brands of hybrid inverters. In fact, in Australia now, hybrids are becoming extremely popular even when people aren't installing batteries because the price difference is very small. So if you want to be battery ready, why not just put a hybrid inverter in and think about batteries later? Now, there are some catches with that, which is often they've got a very small range of battery choices and they may not be available in a few years' time. Something I've discovered many times with the systems here, where I've said to the supplier a year or two later, okay, have you got a battery for that inverter you gave me? And they'll go, oh no, we don't make that battery anymore. We'll have to supply with a new inverter and a new battery. So they're often quite closely coupled. So I guess I warn people that I wouldn't put in a battery ready system and hope that in 5 years' time you'll have a battery to connect to it. So looking at some system diagrams here, these are my little kind of simple single line sketches. So trying to keep it non-technical. So this is an example of a DC coupled system. Now I'm just going to switch to my drawing pad. So hang on, see if I can get this over. There we go. I'm on my drawing pad. Whoops. Let's get a pen out. There we go. So this is the hybrid inverter here. And you can see it's an all-in-one because it's got solar panels connected to it, it's got batteries connected to it, and it's got a load center or a switchboard. Basically, you know, the power center of your home is the load center. It's got the utility grid over here. That's the utility grid, a pole with a transformer on it, and this thing called an energy meter here. So the energy meter is not the utility meter. You might notice I've drawn a little Wi-Fi symbol that's communicating across here. That's not really going to be Wi-Fi. Generally, it's a wired connection, but that energy meter is something that's provided with the hybrid inverter. And the reason for that energy meter is so that this system can see energy transfer with the grid. So it's pretty important that it can actually see where the energy is going and therefore make decisions about, you know, if you are exporting. So let's say you're producing 5 kilowatts of power and it's flowing, some of it's going to the loads. So let's say 1 kilowatt is going to the loads and the other 4 kilowatts is going out to the grid. Unless you're getting a higher rate for your electricity that's being exported, you're kind of missing out on the opportunity of capturing that and storing it in your battery. Now, because this energy meter here, whoops, this energy meter here can see that, that 4 kilowatts flowing to the grid and communicate that back to the hybrid inverter then can go, oh, okay, there's an opportunity to store some of that surplus energy. So going backwards a little bit, so I'm just doing the undo button here, it's a bit slow. It's going to divert that energy, that surplus 4 kilowatts of power into the batteries. And therefore the solar is supplying the loads first, the batteries second, and only when the batteries are full would surplus flow out to the grid. Now the reverse situation here is that it's nighttime and there's no sun, but you've got a full battery and you're drawing power from the grid. So now the energy meter can see that you're drawing a kilowatt from the grid. And at that point, because it's communicating that with the hybrid inverter says, oh, I can do that. So it displaces it by exporting a kilowatt to match from the battery to the load. And so the exchange with the grid now is 0 kilowatts. So it's using that meter to effectively see the energy exchange with the grid and to make decisions about whether to charge or discharge a battery. So that's a DC coupled system. Now you might see it's called DC coupled system number 3. I've actually drawn loads of different configurations for them, but this is just one of a few. The pros and cons in summary is it's simple, all-in-one design. It may charge the battery without the grid, so it actually doesn't matter if the grid's not there. If the sun's shining, it will still charge that battery. The cons are you do require that energy meter. Generally, that comes with the product. So most of the hybrid inverters that have the ability to support loads in the home will have a energy meter, you know, typically a 2, 3 or 4 pole wide DIN rail mounted meter with a communication cable connected to it. And in this picture, it only supplies the load when the grid is present. So there's no backup being shown in this picture. The reason for that is that the single port connection with the grid is what we call in Australia, a 4777 compliant connection. That's our grid standard. Any inverter that connects to the grid must have a safety feature that if the grid's not present, it disconnects instantly within 2 seconds. So if the grid disappears, it turns off its output instantly. So even though it can still charge the battery, you can't use the power in this design. Now there are solutions to this, but this is not, you know, there are systems that are designed to work just like this. They're only for self-use. So this is kind of part 1 of answering the question, David, that your participant asked. So there are some systems that only can do self-use in parallel with the grid being present. Okay, so let me just jump out of that.
Glenn?
Yes.
Okay, well, there are some questions about what you just showed us here.
Okay, go ahead.
I will unite some. The first question: if this function is changeable, if you can change it, if it's something you can configure, and also if the energy meter comes with the hybrid inverter, and if you are talking about a special brand, or if it is something generic?
Part two of your question about that energy meter, generally it is not generic, so it will have a communication protocol, generally RS485, but the actual measurement units, etc., will be a little bit proprietary. So generally the hybrid inverter will come with that energy meter or specify which particular brands and models that it's compatible with. From my experience, they almost always come with one. So it's only on the commercial scale systems I've had to supply them separately. What was part one of your question?
Part one was if these functions, if you can configure it, if you can change them, for example, the priorities for the solar energy.
Right, yes. Now we've actually got three sources of energy. So we've got grid, we've got solar, and we've got battery. And most hybrid inverters have the ability to have some control over that priority. Now, generally the principle is use the free energy first. So solar is the most free energy. It's use it or lose it. So solar is prioritized. Grid, well, it depends on price. So but energy that you put into a battery is no longer free energy. You actually had to purchase the battery. And so there is a cost of electricity coming out of batteries proportional to its storage capacity, its price, and its lifetime. So the energy in the battery is a bit more precious. So it depends on the price difference between the grid and the battery, which one you would prioritize. So you may even have different time of use tariffs from the grid. So here in Australia, there's a huge range of tariffs. I think we've got over 2,000 tariffs in Australia. True. I know that because our software has to model them. And so in some jurisdictions, there's a 4-to-1 ratio between off-peak and peak. So when you've got off-peak electricity that's extremely cheap at nighttime and extremely expensive in the afternoon, there's an opportunity to use grid power for battery charging as well as solar and shift that cheap electricity into the peak pricing time of the day and displace peak pricing electricity with cheaper electricity that you stored in your battery. So those are all configurable options, often referred to as time of use charging or discharging. So you can set windows. Now, a lot of these are specific to the product. So if you want to do this, it's something you'd want to question the supplier. Does your product have this feature? But essentially, it's playing with those three options, whether it's grid, solar, or battery as the source.
Okay, great.
Any other questions?
You actually also answered the next question, so very good.
Okay, cool. All right, I'm just going to go back to my next slide, and I think I've given the summary. You've already given that summary of simple all-in-one. Yep. And now we're looking at something that has a backup capability. Now, a system that has backup can be done in many different ways. And the diagram that I've drawn here is showing what's known as an automatic transfer switch. An automatic transfer switch, sorry, I'm just going to switch over to the drawing board, is a device that can disconnect power. It's operated by the grid. So when the grid power is there, it's in one position, or voltage is there. When the grid voltage is not there, it's in another position. So it automatically transfers across. It also allows the hybrid inverter to detect the loss of grid and to reprogram itself. Now, I've used an Australian term there. 4777 is our grid standard. So that port normally is a grid paralleling port, but whenever the grid fails, that port can become a standalone port. So it can go into what we call standalone mode. And it can only do that when it's isolated from the grid. And therefore it can support a backup load center or switchboard when the grid fails. So there's an external device, in this case called an automatic transfer switch, that's added to a hybrid inverter, just like the previous hybrid inverter I drew, but it has to have extra software features inside that inverter. that allows it to operate in backup mode. So there's quite a few brands that can do this. I'm just trying to think off the top of my head. Fronius, for instance, that the Fronius Hybrid works in this mode. The SolarX 3-phase works in this mode. Yeah, there's a few, but anyway, it gives an extra ability to the inverter to work as a backup system, as well as a grid tie system, as well as a self-use system. So that's the advantage of having this ATS built into it. So got a lot of buttons to press here, sorry. So the pros and cons of this system is it does provide backup power. Now, a warning I give to people when you promise that it does backup is that you've got to specify what the limitations on that backup are. The inverter might be called a 5 kilowatt inverter. That's often its AC output power when the grid is present, so it can export 5 kilowatts of power. But when it's running in backup mode, often it's different. It's not necessarily symmetrical. So some of them are half or even less their grid feed capabilities. And also it's an absolute number too. So if they say it's 2,500 VA, so approximately 2.5 kilowatts, it's 2.5 kilowatts. There isn't much headroom for overload. And many appliances have a surge when you start them, like pressure pumps, compressors, old fridges. So you turn on something, it draws a high amount of power for a few seconds, and that may cause the inverter to shut down. So generally, when you're offering a backup solution with a hybrid inverter, particularly those which are transformerless topology, which have very limited surge ratings, it's a fairly small amount of backup that you can offer as power. It's often a good idea to have a dedicated circuit for that. So it might just be the light that's in the home, or the fridge, or the kitchen, or no, not the kitchen. The kitchen's your worst nightmare. It's where all the power gets consumed in a home these days. So you probably want to differentiate which circuits are being supplied in backup. I've even seen people just put a single socket outlet on the wall next to the inverter and label it backup. And in a way, that's your emergency power. And you're going to get an extension cord, plug into it, and then decide what to do at the other end of that extension cord. So that's your backup capability. Now, there are some inverters that have that ATS built in, that automatic transfer switch. So here you'll see, I'll just go back one. Automatic transfer switch is an external product. So generally another box on the wall, another lot of work for an electrician, or it's built into the inverter. The advantage of building that automatic transfer switch into the inverter is lower installation cost and often faster switching. So they may provide you with virtually uninterruptible power. We're talking, 10 to 20 millisecond switch over time. So those internal ATSs make for a simple installation, and it means you've got a dedicated port on your inverter called backup, or EPS, Essential Power System. So just to summarize there, it makes for a very simple installation, but as with the previous example, generally transformerless hybrid inverters have very limited backup capabilities, so not necessarily the same as their AC output power, though that's not always the case. So you've got to check what their backup capability is separate from their grid feed capability. So how are we going, David? Any more questions?
Yes, Glenn, we have some questions, but actually I think we can leave them after it, because the first one is more or less about how the grid and the distribution companies work together, and the other one is about costs. I think we can leave it for the final questions, right?
Okay. No worries.
Oh, there's just some asking which companies or which brands actually include the ATS in their hybrid inverter.
Well, I'm just thinking around my lab. Goodwe,
Okay.
yeah, Selectronic, SMA Sunny Island, Schneider XW Plus and XW Pro, Studer, Tech, Victron, There's quite a lot.
Okay.
And whether those can be installed on grid or not depends a bit on your utility rules. So some of those in Australia can't be used on grid. For instance, the Sunny Island inverter doesn't meet our grid standard, even though it works beautifully in a microgrid situation, which is how I use them. It doesn't have the software features required for VAR volt and VAR watt mode that we require. Okay, shall I move on?
Okay. There's just, they are now starting to ask.
Yeah, good.
What do you think about the, for residential use, the lithium batteries with high voltage? Do you think they are they are better and more reliable, or do you have any other recommendation?
Yeah, so what we're seeing is a move towards higher voltage battery systems for hybrid. I'm talking 400 volt batteries typically, or 2 to 400 volt. The reason for that is cable size, efficiency. Also, the inverters are less expensive and lighter. So when you have a battery that's operating at extra low voltage, say 48 volts, the inverter has to step up to its DC bus, which is typically around the 400 volt mark. And to do that generally is done with an isolating transformer, and it's heavy and expensive. It does come with some pluses though. It gives you some thermal inertia, which is good for surge demand. But for hybrid systems, we're not so much concerned about surge demands because most of the time it's running in parallel with the grid, so the grid can cope or provide that surge. You're looking for lower cost, higher efficiency. So transformerless inverters will work most efficiently when they're not doing a big step up, so that the battery voltage is very close to the internal bus voltage of the inverter itself. And so batteries like LG Chem's 9.8H, it's a 400 volt battery. Some come stackable. I've got some Pylon Tech batteries here that are stackable in 50 volt modules up to whatever you need, up to 800 volts or more. Particularly for three phase, you want a higher voltage. Yeah, so I think high voltage batteries are probably the way to go for hybrid, and also for just big systems. So, you know, I've got a 30 kilowatt three-phase system here that's running on 48 volts, so the current is a bit mad. When you start to get large amounts of power, you want to have higher battery voltages to keep your cable sizes in check.
Okay, great. I will just leave some of the questions for later on, I think. Okay. I'm writing them down.
Now here's a DC coupled system and an AC coupled system. Now I haven't talked about AC coupling yet. I'm sort of jumping a little bit, but what we're looking at here is two systems installed in parallel. So you don't actually have to have one or the other. So let me just see where my drawings are. Got two computers here, one with the drawings of these so I can sketch on top of them. The ability to add in parallel another system is pretty desirable. So I'll cut to it. There we go. So we've got, let's call this a hybrid inverter system that's been installed here, and the customer's very happy, all works well, but then they just want more solar. They don't want any more batteries, they want more solar. Now, you may have maxed out that hybrid inverter with solar. Say it can take, let's say it can take 7 kilowatts or so of solar. So we've got 7 kilowatts of PV power on that hybrid inverter. It's got 5 kilowatts of AC output. The battery system does what the customer needs, but they actually want more solar for self-use during the day, for instance. And what we're doing here is adding a second system, which is AC coupled. Now, the terminology coupling is about how does the energy traverse from the renewable source, in this case solar panels, which are DC, to a battery, which is DC. And you'll see the line here is orange, that's a DC cable. The lines that are blue are AC cables. And so it's got to go through the AC network. So it's getting a bit messy. Let me just get rid of those. So for an AC coupled system, it's about sending power through the AC network to the battery across the blue lines. And because this is possible, and it's possible because of this energy meter again. The energy meter allows the hybrid inverter to see that surplus solar. Some of them even have multiple CTs. They might have a CT around the output of the solar inverter, but it doesn't actually have to have that. It can work quite fine, because if I was to do a situation where it's daytime, the sun's shining, so let's say this system is a 6 kilowatt PV system, and it's outputting to the grid, let's say 4 kilowatts, and we've got maybe 1 kilowatt going to the loads here, like this. Because of this energy meter, which is coupled to the hybrid inverter, it tells the hybrid inverter, you're losing 4 kilowatts, you're giving it away. I'm not sure what your feed-in tariffs are like, but in Australia, they're never as good as using the energy yourself. So we don't want to send it out to the grid. And the hybrid inverter can see that opportunity now and can choose to charge its battery at whatever rate it wants to, up to its maximum power rating. So now what happens is, rather than spill that energy to the grid, it draws that energy back to its battery. So it's charging the battery at 4 kilowatts while still supplying the load at 1 kilowatts. There we go. So that's adding another inverter, a grid tie inverter, to an existing system. It could happen in the reverse order, by the way, which is more common in Australia, where people already have a solar inverter and battery, sorry, a solar inverter without battery, and they want to add a hybrid system. So either way, you can still utilize the energy from both sources. So a little bit of a summary there. You can charge the battery from both solar sources, but it does mean you've now got 2 inverters. So the IES capacity, or inverter energy systems, the sum of all inverter energy, has increased to double what it was. So maybe these are both 5 kilowatt inverters. We now have 10 kilowatts of IES capacity. Why this is a consideration, in our standards, we actually have some notional limits. They're actually quite conservative. So for a single phase installation, we're only supposed to have 5 kVA of inverter capacity per installation, but the utilities are allowed to override that and let you have more. It's up to them how much inverter capacity they're willing to have on their networks. And the rationale, this is getting a little bit technical, is to do what's called hidden load. They're worried about the amount of hidden load that's hidden by inverters when it's sunny that could suddenly disappear due to power quality issues on the grid. And hidden load means it suddenly appears to them whenever there's a disturbance on the grid, say a frequency or voltage disturbance, or even just sudden cloud cover. All that load on every single system on that part of the network comes back onto the grid at the same time. There's no diversity factor. It's all synchronized with the grid power quality or the solar source. And therefore, they've got to be able to cope with that step change. We've had a few incidents in Australia where the grid's fallen over because of that. We had one state, South Australia, lost power for 3 days. That was actually wind turbines going offline all at once. But now that we've got 12 gigawatts of solar on our network, if there is a frequency disturbance and they all were to turn off at the same time, there'd be 12 gigawatts of hidden load magically appear, and it'd be lights out Australia. So that's one of the issues with sum of all capacity. So let's just run over AC coupled systems. The pros, and by the way, AC coupling has become extremely popular because its simplicity is very easy to do. It was sort of pioneered by SMA with their off-grid systems using Sunny Island and Sunny Boy inverters, but now just about everyone's doing AC coupled options in various forms. The pros are it scales very easily. You can have multiple systems coupled together onto the same AC network. They don't have to be in the same location. You don't have to have your solar panels near your batteries. They could be separate systems. You can have a solar inverter on one building and a battery inverter on another building, and they're connected but to the same AC network. It's simple to install because you're generally just working on the AC side, installing a new circuit. So there's not a lot of DC cabling and configuration, no shunts, etc. And also it's quite low cost, especially for systems over about 2 kilowatts or so. And if you're really worried about efficiency of use of solar, it's most efficient for daytime use because the energy is being converted at a high efficiency rate by these solar inverters and going directly to the loads, not through a battery inverter, through a battery. There's no double conversions. If you're off-grid, there is a bit of a con with AC coupled systems is what's known as the black start problem. If you have a battery inverter that shuts down because the batteries are low in the middle of the night, your solar inverters will shut down as well because they require that synchronization to the battery inverter. And so when the sun comes up in the morning, nothing happens. You have to start a generator or some other way of charging those batteries. They do take up more space because you've now got two inverters, a solar inverter and a battery inverter, so physically a bit more spacious. And if you're off-grid, you probably need a proprietary solution so that they can be power ramped. That's a little bit technical, but yeah, off-grid AC coupling is a little more complicated. So there's an example of an AC coupled using SMA products, the Sunny Island being a battery inverter and the Sunny Boy being a solar inverter, the red one. They can share power across an AC network. They can work on-grid or off-grid depending on your grid standards too. Okay, how are we going, David?
Very good, Glenn. No further questions right now.
Okay. So I might just go a little bit faster at this point because I just looked at the time. So we might have to do this in two parts, you know. There's quite a lot of content. And you've asked some great questions. That's what it's all about. So this is an AC coupled system that I just gave a similar picture, but you'll notice there's no solar on the battery inverter. This is just a dedicated battery inverter and a dedicated solar inverter that are working together on grid as effectively a self-use system. So it's non-proprietary. AC coupling on-grid generally means that they can be any product because they're just sharing energy. They don't have to control each other. They can be easily added. So you might start off with just a solar inverter and then the customer says, and I want batteries. Well, you don't have to add the batteries to the existing solar inverter. You put in a separate battery inverter. And to use brand names, Tesla's probably the most well-known battery inverter in a box. So it's a 5 kilowatt inverter with a 13.4 kilowatt hour battery in a single box, and it's a retrofittable solution to an existing solar. There are other products that work similarly. It does add to the IES capacity, and in this particular drawing, it only works when the grid is present. There's no backup circuits drawn in this particular configuration. Now, this is probably more common configuration for off-grid, but it can be done for on-grid as well, which is where you put the battery inverter, one which has two ports. It has a grid port and a load port or a backup port. And you'll see that it sits in the middle between all your essential loads on the right and your grid-only loads on the left. It allows it to effectively have uninterruptible power to that load center on the right, because it's all the time supplying that load center in parallel with the grid. If the grid fails, you still have continuous power. There is a tiny transition, which will be to do with a voltage step change when the grid goes away, but it gives you a pretty reliable source. Now, this is also more common in an off-grid design where instead of the grid on the left-hand side, you'd have a generating set as your backup source. So AC coupled systems can work on-grid and off-grid, but if you're off-grid, we do have an extra requirement, is that the battery inverter can stop or curtail the production of the solar inverter. Because if you've got no grid to spill surplus energy to and your batteries are full, how do you stop the solar working? How do you ramp it down? And that's where proprietary solutions using either communication cables or frequency shift power control comes in to control the output or curtail the production of the solar inverter. Okay, it's going forward. So the pros and cons here. Now the solar works without the grid. So if the grid fails, the solar will still synchronize with that battery inverter and charge the battery. Though at some point, the battery inverter will kick off the solar inverter once the battery's full. It has to stop it somehow. So the crudest way is just raise the frequency and stop it producing in parallel. No energy meters required because the battery inverter effectively is measuring all the energy flow through the load center. There's a small con, which is the transfer contactor limits within that battery inverter will determine the maximum demand that the load center can have. Though many battery inverters have the ability to have external contactors, so that can be overridden. So that limit's sort of not really a big deal. And it requires control of the solar inverters when the grid's not present if you want to have smooth charging of those batteries. So it's not really a requirement. You can just sort of like charge them up to 80, 90% and then kick the solar inverters off. This is a bit of a fun one. I call it the death spiral accelerator. The name came about because in Australia, people were talking, or utilities were talking about the death spiral of their business model, which is, you know, as more people put solar on and use less electricity, to recoup their investment, they have to raise the price of electricity. And as you raise the price of electricity, more people put solar on and use less of it. And that's a death spiral. So I call this the death spiral accelerator because it makes it very easy to have an independent system that is not limited by any utility rules. Because if you look at the system that I've drawn on the right-hand side, it says, it's got a little line there, blue line with an arrow saying charging only. You're just putting in a system where the grid is just a charging source. You're not interacting with the grid. You're not paralleling with it or exporting to it. So there's no interaction with the utility with another generator. You're only a load. And therefore, there's no, in Australia anyway, there's no restriction on how big that can be. So there are some products on the market that are really perfect for this, and they're very cheap. MPP Solar, the Outback Alino, these are products specifically designed to work like this, using the grid only as a battery charging source. Anyway, there's a bit of a fun one. Now moving on, I'm moving to a different topic, just sort of still in the hybrid world, talking about system sizing. So this is more a design consideration. And now if you've got this is the domestic system, the blue area is the customer's consumption, the yellow area is the energy from the sun, and the green area is energy from a battery. Now you'll notice that the battery energy is being used at nighttime, so it's charging during the day, but being reserved to only be used at nighttime. Now that's a decision in the software for the hybrid inverter. You could say only use the batteries when the solar is not enough, and therefore prioritize solar to cover the loads. But you'll notice that the green area only goes up to 3 kilowatts. The reason for that is that the output power of your hybrid inverter will determine the level of support that it can give to the loads. So in this home, the loads are going up to 6.5 kilowatts in the evening. So I'm still using grid power for some of that. So that's a consideration. If you want to have self-consumption 100%, you've got to make sure that the ability to support the loads is suitable for the maximum demand of the home or business. The other consideration is how big in capacity is that battery. Here we've got a system that the red line is showing state of charge, and the battery is charging up and it's fully charged by just after midday, and it's sitting at 100% for some hours. You could say the battery's too small. You're spilling solar or curtailing it. So you might be spilling it to the grid, or it's being curtailed and not produced. It's not wrong though. This will work fine. It's just that there's a missed opportunity, and that could be a cost decision. How big a battery? You don't have to capture all of the energy from your solar. And this is me logging my house. Now, the reason for this picture is when I draw pictures like the previous one, I'll just go back to the previous one, pictures like this, they're always kind of woofy lines that look all, smooth or relatively smooth. But when you look at the real generation profile of a single installation, it's very digital. See how those things just turn on and off. And that means that not all, generally inverters can't respond fast enough to support those digital spiky loads fully. So even though you've told it to use batteries and solar first, and even though your inverter has the ability in terms of power rating to support the loads can come on too quick for them to respond. So generally there's a response or time of 10 to 30 seconds. So they try to ramp up to meet the load and displace the grid power, but some things turn on and off very quickly. So those spikes can be the reason for still some grid consumption, even when you think you've got enough battery and enough solar. I thought I'd just touch on a couple of other considerations once we're moving away from batteries for a minute. Solar panel optimizers. Solar panel optimizers are quite a big part of the market, certainly in the commercial area here in Australia. The reason for that is that they make for very easy design when it comes to complex roof arrays, where you've got panels on different orientations, different shading conditions across the roof. And there's also a bit of a safety boost in that you've got control over the DC voltages on the roof through individual power conversion devices on every module. This is a Solar Edge brand that I've shown here in a Tego in the left-hand side. They both work in similar ways, which is they control the ratio of voltage and current coming out of each panel and supplying it to a common string of modules or string cable. These devices mean that you can actually have different power ratings on your panels. You can upgrade them piecemeal. You can have different orientations on every panel, and any shading on any one panel is only going to impact on that one panel. So solar panel optimizers certainly have their place. This is actually a house on my microgrid, which is my next door neighbour's house, where we put some optimizers on. You get so much data. It's more of an engineer's tool. You can see how every single panel is performing compared to every other panel. And if you look at this picture here, you'll notice that the fourth panel from the left is dark, meaning low production. And you can see why, because directly below it, the house, which is facing north, has got shade on that fourth panel. But it doesn't matter. So I'm not sacrificing the whole string. Only that one panel is getting some lower production values because of that localized shading. So that's a big plus with module level power conversion equipment. You can also do it in the AC world with microinverters. So here's some pictures of different brands of microinverters, though I think probably the only one that you can get still is the N-phase one there on the bottom left. I don't know if SMA actually ever released their microinverters, and a few other ones there have gone out of business. So that microinverters work similarly in that they control every panel independently of every other panel, but instead of outputting onto a DC string, they're outputting onto an AC trunking cable. So they give the same benefits of module level power optimization and safety, because there's no high DC voltages on the roof. Just one panel is the highest DC voltage. Now, David, I'm looking at the time, it's 10 o'clock, and I just realized that I've got too much content to cover, but I was going to talk about the battery standard, but it's probably another half hour. I'm happy to do another session, if you like, and focus on battery safety.
Yeah, possibly would be, if it's not bothering to you, I think it's a great idea, because yeah, there's a lot of content, as I can see.
Yeah, I'm actually only halfway through.
Okay. And, yeah, so we could if you're good with it, we could just do some questions we have.
Yep, let's do that.
I think there were several questions, so we better take that time and we agree on a new day. Okay, so let me just look for the, yeah, okay. There was one question, I think, which is very important. I don't know if you will take it in the next turn, let's say, but it's about, there's several questions in one regarding how the grid and the integration with batteries works in Australia. The first question, if actually the distribution company or the electricity seller can offer the same services as you can offer with the batteries, if there are some restriction for distribution companies to work on complementary markets. I think the question is going on, how is the electricity market structured actually, and who can offer which services?
Yes, so we call it ring fencing, which is that there's a sort of an economic fence around different parts of the electricity network. You could roughly divide the electricity network into generation, distribution, and retail. And for instance, the distribution business model is utilities. They can't directly compete to the customer level by selling a product such as battery systems. So they're kind of restricted, but there's kind of edges to it. So in some jurisdictions, the utility is providing some of those solutions. Australia has 29 utilities, I think, and some of them cover kind of special areas which really no one else wants to cover, like Western Australia. I mean, it's a third of the area of Australia. Horizon Power, who's the utility, has 22,000 customers. But it's a third of the area of Australia. So you can see that the remoteness is the problem. So yeah, they provide solutions for their network, even though generally that's not permitted because of competition law.
Okay, so there are several restrictions in that case for the utility. Okay. And what was the oops. Yeah, and in the same question, the people asked me if what was the main change in your in law or in regulation which made it possible that solar energy grew that much in Australia?
A few factors. There was some government incentives, and they've varied over time, but starting back in 2001, there was a small incentive program. It took a big jump in about 2007, where people were given $8,000 government funding for a 1 kilowatt system. Amazing. So by about 2010, you could offer people a free set of steak knives and a solar system and still make a profit. So that was a very overheated rebate for a short period of time. But then they moved to a different model, which was a trading system using trading of certificates for renewable energy. So they introduced the renewable energy or small-scale renewable energy scheme, which was systems up to 100 kilowatts. You got certificates that represented the amount of renewable energy produced in advance over the next 15 years. And so you could claim in advance 15 years worth of production. And they even had multipliers on that initially. So you got up to 5 times multiplier on the production of the system. And those certificates could be traded on a market. And the government required all electricity retailers to purchase a certain proportion of their electricity as renewable, or at least to supply a certain proportion as renewable. So mostly they would buy certificates. So that incentivized domestic and commercial solar strongly. There is a separate scheme for over 100 kilowatts called the large scale generation scheme. And it's based on production. So after 1 year of production, you can claim or create the certificates for that system and trade them. So those two things generated a lot of growth in the market, but then the price of solar has been the other big player. It's come down so much. So we've got the scale has brought down price, the manufacturing costs from the source, and the efficiency of our market. So installers are very good at installing systems at around about $1 a watt in Australia. So that meant that for the domestic market, installing a 5 kilowatt solar system is almost something you can put on your credit card. It's just a discretionary purchase. It might be $2,000 to $3,000. People go, yeah, I'll get one. So yeah, it's become extremely affordable, and as a result, we've got a massive growth.
Just trying to get it right. So you mean for a residential solar system, I can actually receive all these certificates in advance for the next 15 years, and I can commercialize them right now when I first install the system?
Well, actually, the program ends in 2030. So right now you get 10 years worth of advance. So initially it was 15 years, but now it's each year it's dropping back until 2030 by 1 year. So that's right. Your certificates are issued on the moment of installation, or created is the word, usually the retailer of the solar system will credit those certificates to you. So you don't actually have to go and trade them.
Okay.
It's done by your electricity, your solar installation company. They'll discount your system for those certificates.
Okay, that's very interesting. That's something. I think there's a certain scheme that starts to work in Chile. It's very new actually, charging for emissions, and renewable energy systems can apply for that, but it's still very complicated actually. And it's interesting to know that it's one of the driver in Australia. I'm sorry if I from time to time change the topic, Glenn, but it's difficult to listen to you and to read the questions. So another question that I read was which type of battery you actually would recommend, or if you basically go with the lithium ion.
Okay, so this is probably a better answered when I do my second part of my presentation, which is all about batteries. But there is, at the moment, a huge growth in the range of technologies of energy storage. You could think that lithium is kind of the future, but actually lithium is probably the short-term future. There are many other technologies showing great promise as well. So in my lab, I've got molten salt batteries. I've got a range of different lithium chemistries, lithium titanate, nickel, manganese, cobalt, lithium ferrous phosphate. I've got flow batteries, which is zinc bromine. I've had aqueous ion batteries. I probably missed a few, but yeah, so there's a lot of different chemistries that have different niches. So lithium these days is very popular for energy density. It's light, compact, suits small scale applications, has high cycle life, but there's safety issues which are still a concern. So hence our battery safety standard is really pretty tough on lithium batteries. In fact, you have to put a fire barrier when you install one in a home now, if there's a habitable room nearby. But when you get to utility scale storage, there's other options as well. So that some things work better at scale than small scale.
Okay, great. Thank you very much. Okay, yeah. Well, you already answered somehow the question about costs, but possibly I think that when you talk about $1 a watt, that means only on grid, right? What is the cost range for hybrid system?
Okay, so probably a way of looking at a hybrid system is what's the levelized cost of electricity coming out of a battery. So levelized cost of electricity is based on the purchase price over its life, the energy it will deliver over its whole life compared to its purchase price. And what is the life of a battery? There's different ways of determining that. Some people will do it based on the cycles that you'll get out of the batteries. Others will base it on the warranty. Now, to be honest, the warranty is probably the only one that you can really sell it on, because if you say, oh, it'll give you 20,000 cycles, but it'll only last 10 years, you're unlikely to actually get 20,000 cycles in 10 years. When you look at the life of a battery versus the amount of energy that you can shift through it, will give you a cost of electricity. So that levelized cost of electricity model is a good one to look at. At the moment, from my modeling of a lot of the commercial residential systems here in Australia, the payback is often never. So it's, the warranty period will probably come up to its limit before it's actually delivered the cost savings of the purchase price. So yeah, the installation cost, well, lithium batteries are around the $1,000 a kilowatt hour. So it depends on how many kilowatt hours of storage you want. So that's kind of a ballpark figure, though that's dropping all the time. Low would be $600 a kilowatt hour. High would be more like $2,000 a kilowatt hour, depending on the product.
Okay, great. A short question was about for this model AC/DC coupling you showed us, and the use of different inverters and energy meter. Is it necessary that they are normally from the same brand, or is there also, can it operate with different brands?
So if you're talking hybrid on grid, with AC coupling, there's no need to use the same brands. So the battery inverter and the solar inverter can be completely different products. The fact that the battery inverter has the energy meter means it can see the exchange of energy with the grid and make decisions to maximize self-consumption. So yeah, there's no need to combine the two.
Okay, that's great. Yeah, that's a very interesting one too. Considering these systems, which components you think are most probably to have some guarantee or some technical issues?
There's actually a government-funded battery test facility in Australia called the Battery Test Centre, I think it's called. Battery Test Centre, yeah, in Canberra. And they've been running long-term modelling of most of the major brands on the market for about 3 or 4 years now. And they've got some wonderful data. It's all publicly accessible. And so you can kind of see which products have delivered what they promised, because it's really hard, to take something from a manufacturer and, believe those promises when there's not a test standard for them. But that's something we're hoping to fix at the moment, which is I'm involved in the committee that's writing a performance test standard for batteries, so that we can actually have a way of comparing brand A and brand B based on capacity and cycle life, etc. So yeah, I can't really give an answer on which ones are good. I often jokingly say, I'll tell you in 10 years' time.
Okay. That's really interesting. So this test center is actually funded by the government, and I guess then it's public information, right?
It is. I'm just trying to look it up now.
Okay. Should do something like that in Chile too, I think.
Well, it's probably the same products too. So hang on, I've got it up here for you. I'll just share it. There we go. So that's the facility, the battery test center.
That's very good. Yes.
But it is only, it's called a lithium-ion battery test center, but they actually test batteries other than lithium-ion. I don't know why they've got that name. Yeah. So you'll see lead acid, zinc bromine, aqueous ion, and they've got real-time live data too. So they shift the energy between batteries and just all the time cycling them. So you can pick your favorite product and see what it's doing right now. So there you go. There's the Tesla Powerwall, and there's all the other batteries currently on the test rig running. But they've got historical data, so you can see when a fault occurred, what the manufacturer's response was, how much capacity fade over time. That's really interesting. There's the capacity fade. So, some batteries look great when you buy them, but the promise of 80% after 10 years is not going to be realized.
Yes. Glenn, just as we are looking at the lithium-ion battery, the lead acid typically was very sensible to temperature. What would you say about the lithium battery? Is it do they have problems, the same issues, or is it quite different?
Yes. So, sorry, let's bring my other slide back. I was going to talk a bit about temperature, but I guess a summary is that every technology has its temperature profiles that it prefers. So lithium, actually cold is a problem, whereas lead acid heat is more of a problem. So lithium batteries have a kind of narrow window of safe operation. So it might be below about 5 degrees Celsius. Their charge rate may have to be curtailed significantly because it's difficult to charge them when they're cold, though discharging them, not a problem to quite a low temperature. So it's depending on where you're charging or discharging them. At the other end of the spectrum, they're quite tolerant of heat. So they're often rated to 50 or even 60 degrees Celsius, but they will age more rapidly. So most battery technologies don't like heat in terms of lifespan, whereas lead acid, very intolerant of heat, will cope with cold down to the freezing point of the electrolyte.
Okay, great. Thank you very much. Then we have some, I think we're already getting to the last questions. and that's very good. And
The last question.
last question. Are you already tired, Marcela?
Yes. No, no, no. It's the time.
Okay, great. I would like to make two questions. One relating your presentation and one relating the photo of your house, actually. So the first question is regarding it goes a little bit into the virtual power plant issue, and the first question is which are the mechanisms so your solar system actually could know the price of the grid? Is it manually, or is there any software that actually can operate it on its own? And so I make it one question. Are there some technical issues right now in the use of these virtual power plants?
Okay, excellent question. So there are different markets for electricity in Australia. The simple retail market is you're given a price. It's probably time-based, so there might be an off-peak price, a shoulder and a peak, or it might just be off-peak and peak. And therefore, it's going to be time-based. And therefore, you can program those times into the inverter. If you want to use prefer off-peak electricity at a certain time and then battery energy instead of peak at another time. But then the wholesale market operates on a 30-minute window, and the 30-minute pricing varies dramatically. But
yes,
you have to be a retailer to enter into that market. So customers can't buy and sell into the wholesale market. However, we've got aggregators who aggregate customers together who have battery storage and have a product that interacts with the wholesale market. Reposit Power is probably the most well-known in Australia, and they watch the price on the grid. When it hits $1,000 a megawatt hour, then they let all their customers sell energy at $1,000 a megawatt hour, which is $1 a kilowatt hour, so quite a good rate. But that might only happen a few times a year. So it just depends on whether there's a heat wave or something that's causing the price to spike.
Okay, yeah, that's a really, I think we can go deeper in that the next time. And well, before we finish, my last question is in your house, I saw you have the solar thermal panels also installed. And it's a question that has nothing to do with your presentation. Yes, there it is. But actually there's we as ACESOL, we have several problems, because in Chile, in the use of social housing, these vacuum heat pipes have been prohibited, that's the word, I think. Because we had several problems because they got too hot and there was a lot of vapor or something like that, and so they did not change security issues, but they completely forbid the use of it. And what is your opinion about using heat pipes in hot areas?
Okay, so I've got both systems on my roof. If you look at the second story of my house, on the right-hand side is evacuated tubes. So that's a 30-tube system. And on the left-hand side is 8 solar panels tilted up. It's a water heating system as well. So it's electric water heating from PV panels. The difference is that thermal systems, particularly evacuated tubes, which are very efficient, are often about 60% efficient at converting the solar energy into heat. Whereas a PV panel is about 20% at best at converting solar energy into electricity and then into heat. So you need about 3 times the roof area. So you might think, oh, that's no good. But actually, it's about 3 times cheaper. You don't need to hire a plumber, which is an expensive trade in Australia. You don't have to buy copper pipes, which are expensive. And for me, one of the biggest benefits is the performance is better the colder it is. So in cold winters, sunny days, the PV works really well, better than it does on a summer's day. Whereas the evacuated tube will start to due to heat differential and also pipe losses, drop off a bit.
Okay, so that is a nice topic for our technical solar thermal committee we have each month. So thank you very much. Okay, so that was our last question. Glenn, I really thank you. It was very interesting for me. It was a little bit difficult switching between questions and trying to understand your presentation, but it was really interesting. We had a lot of participants. Thank you for being with us, and I hope we will, by email, we will coordinate the next time. So thank you very much, and enjoy your day today. I think you're on vacation, right?
No, it's just another work day for me.
No, it's school vacation. I'm sorry. That was what you told me.
Yeah, my kids are home from school. They're downstairs. Yep.
Okay. So thank you very much, Glenn.
Thank you, Glenn.
Thank you,
It's a
Glenn.
pleasure.
Thank you
See you,
very
Marcelo.
much.
Really a pleasure.
Thank
See you,
you so
David.
Great
much.
presentation.
Yeah, Pablo.
Nice to meet you.
Bye-bye.
Bye-bye. See you next time.
See you,
Y
Glenn.
muchas
you.
gracias a todos por
If
estar
you
con
need
nosotros.
anything from Chile, call me.
Thank you. I'd love to.
Bye.
Bye.
Chao, chao. Vamos a compartir después por ACESOL